I'll be talking about joint work with core, so and also referring back to joint work with core and Kari-Kalta. Let's see what I'm to say. I want to remind us of Adler's theorem, the folklore theorem, building on the Renyi work, and then I'll talk about planar extensions, in particular natural extensions, despite what we heard of cries for no more extensions. Continued fractions, one always wants to see more of them, so I'll talk a little bit about some generalized continued fractions. I want to try and argue for wasting many hours of one's life building natural extensions, to talk about their uses, and also I'll talk a little bit about a cute idea of Gore's, I believe, quilting, which Wolfgang Steiner mentioned, and then I'll try and prove something, say. So that's the plan. We'll see how it goes. So Adler's folklore theorem is really, as far as I understand it, it's building on the Renyi result we just heard about. It just makes it a little more useful, more easily applied. Adler introduced this in 75, and then in an afterword to Bowen's post-mortem paper, posthumously published paper, Adler has remarks about the theorem and how it came to be. He calls it the folklore theorem. At that time, people called it the Adler theorem. So there are four basic requirements to get going for an interval map to show that it is in particular ergodic. It has a unique ergodic invariant measure that's absolutely continuous with respect to Lebesgue. And so it's fullness of cylinders, twice differentiability, eventually expanding, and then the distortion bound that Hitoshi was just mentioning. And the plan is, if I don't get too distracted, the plan is to show that if one has a planar extension in the hand, then especially verifying the distortion part can be nice and fairly straightforward. So that's, of course, where lots of time is spent catching that last one. So I have some old figure to warn myself, at least, about using calculations. These are squares, but I ran this in Mathematica. And so this is the Nakada Ito Tanaka natural extension. So it's simply T of x is the regular continued fraction map. X goes to 1 over x minus the floor of 1 over x. And then we have to keep track of the paths in order to have the nice natural extension. The invariant measure was already mentioned. So I have here indicated in red is the cylinder for the first partial quotient being a 1. So it's a full cylinder, and it gets smeared out here. I'm going to ignore those guys. The second full cylinder is the white with partial quotient 2, and then there are countably more cylinders. It all fits together perfectly. Cute idea, no? Really nice. And the fact of the matter is, really, it's the hyperbolic action. It's a diagonal action of SL2R on the hyperbolic plane. It's just a nice change of coordinates to make things work very pleasantly. In particular, what's nice about this choice of coordinates is that rectangles are sent to rectangles. And when you're trying to make sure that things fit together, that's very helpful, as opposed to curvilinear boundaries. So it's really surprisingly handy. So the second coordinate, the map, the y goes to the inverse transpose of the matrix acting. Well, since it's nice to change coordinates one time, why not another? So a very handy choice of coordinates in this situation is to have Lebesgue measure being invariant. So planar Lebesgue measure. Okay, so the formula in the second coordinate now looks a little stranger, perhaps. This cx plus d squared times y minus c times cx plus d. However, I can almost calculate the Jacobian to check that the Lebesgue is invariant here. So we've got a nice Möbius action. The derivative in x here is cx plus d to the minus 2. I'll take the partial of the first one with respect to y. I've got it, 0. So all I really have to care about is taking the partial of the second with respect to y as well. And you see cx plus d squared cancels the cx plus d to the minus 2. And so our Jacobian matrix, I repeat, has a 0 in the off diagonal, has cx plus d to the minus 2, and then cx plus d squared. So Lebesgue is indeed invariant. It's a very handy formulation, although I always forget the second variable's formula. So in the title, I mentioned some generalized continued fractions. Wolfgang was talking about the Hecke groups. So the classical regular continued fractions are, of course, related to SL2Z or to PSL2Z. PSL2Z is a Fuchsian group, a triangle Fuchsian group. It has, first of all, a translation. We like translations to start up, to have some interval on which to set up the continued fraction. We'll bring back into the interval. And then the PSL2Z has an element of order 2. Z goes to minus 1 over Z. And it also has an element of order 3. So it's a Fuchsian triangle group of signature 2, 3, infinity. Let's look at other signatures. So here the groups are of signature 3 and infinity. And so what we're going to do is mimic the situation for continued fractions. So each time we're going to concentrate on any two of these three matrices generate the group. I'm going to take A is the one that's the translation, and then C here is of order 3. So we're going to take a fundamental domain for the action of the translation, i.e. an interval, and we're going to take any x in the interval, and we'll apply this element of order 3 until we exit the interval. There aren't many powers of that necessary. It either happens immediately or after the second power. And then we just pull back. No idea. Yes. So here's the map. So we've fixed one of these groups. So I have a countable collection of groups. For each one, I'm going to have a full alpha interval from 0 to 1 and contemplate what can happen for these generalized alpha continued fractions. So that's sort of the game. Let's see what else is there. Okay, so I repeat, in the regular continued fractions, you take x and you simply go immediately out using basically the element of order 2, and then you translate back in. Okay, here you simply you have some other element of finite order. You apply it until you exit the interval, you pull back in. So we can do this for all the triangles which have some translation in them. It gets quite complicated. So here's the graph of one of these. So this is where the n is also of order 3. So we have a group with 3, 3, infinity, if you like these signatures. And then I just chose some number alpha, 0.14, just to have something to look at. So here's the graph of the function. And it looks like a continued fraction sort of thing. So we have, first of all, we have lots of full cylinders. Of course, we'll have troubles because here is a branch that's not full, or always announces some work to be done. And then, as some of you have noted in the past, there's Carlo. In fact, here's some trouble because this has a bad slope for us. This is not an immediately expansive map. Okay, so we'll have to deal with that somehow. In this case, as I said, we apply this element of order 3 as many times as necessary to exit the interval. So in this case, with alpha, sort of the complement of 0.86, then we have this region is where we have to apply this element C twice over. So you apply it once, and it starts. They try to act like the region for which you apply C one time. So I won't go into details, but it becomes fun to really study the dynamics of all these maps. It's really understand them, to set up the symbolic dynamics, to see the structure. I'm not going to talk I'm not going to talk about that really today. Gary talked about such things in Leiden a year or so ago, whatever the time was. There can't be a talk about these sorts of continued fractions without some pictures of natural extensions. You're very happy to see that, at least my co-author is. So here on the left is this very nice standard measure, the 1 plus xy to the minus 2 dx dy. And okay, I just ran the two-dimensional map over. I took some arbitrary point and just ran it over. The system is surely ergodic. Okay, it's surely ergodic. And so I take any old point and I just follow the orbit. And it's sampling along. And you see there are lots going on there in along here. And that's because this is getting close to the curve y equals minus 1 over x. And that's getting close to putting a 0 in a denominator. And so there's lots of mass in that part of it. So in that case, it's really not quite, it's hard for a naive person like me to just look at it and understand what the measure is of some region if I just take the trace of things. So if we switch to the Lebesgue situation, then of course, it really is what you see is what you get. It's very pleasant in that manner. But boy, when you go to work out to really prove that this is the natural extension, the pieces fit together, this kind is a pain in the neck, if I may speak like that. And it's nice to have rectangles that fit into rectangles. Right? So of course it's the same system, but this is so.
Sorry, I didn't get what was on the right side.
So on the right side, ready? I'm going to try this. You can tell I've worked with core, huh? What do you mean? Okay, I'm ready again. So on the right-hand side, I'm using the Lebesgue coordinate system.
Okay.
Right? Okay, here we go. I was supposed to just stop at the right point. I try some more. There I, oh man. Okay, so I repeat, of course, you run some computer experiment and you say, okay, this must be my natural extension. But you got to prove it, and of course, in this case, there's a countable collection, and then there's uncountable alphas. There's some work to be done to do it in some reasonable fashion, but actually we can. And things have to fit together, and they fit together in a really beautiful way, of course. As you scoot through, there are also here in this situation, there are synchronization intervals, and as you move through, things have to continue to fit just correctly. So there are various bits of the dynamics that are really gorgeous. These are just cute little systems. And the sort of thing I mean is that in order for, let's take minus 2 and minus 3. So these are, the numberings is to indicate the various cylinders. And so you see we're back, this is the alpha equals 0.14. There was a left non-full cylinder. I'm indicating that by minus 1. And here it is, being non-full. This part comes up on the top. And my claim is that these glue, so there has to be the appropriate relation to make this so-called lamination occur. The bottom image here with the, just the corner top there. And then as you move through and deform, which two pieces actually have to laminate together changes. So there's a whole family of relations that have to hold throughout the various synchronization intervals. Okay, I repeat, once one has a natural extension truly, or a planar extension, truly proven to be correct, you've put in so much work, you want to get something out of the investment. That's what I believe I'm supposed to be saying. So what I want to do is introduce a notion of bounded non-full range. My author told me that the idea of finite range I should attribute to Ito Yuri. I just heard in a previous talk that maybe it predates that. I'm not sure. We'll look into that later. But in any case, in finite range, as Hitoshi was just saying, what happens is We have to worry about the case of non-full cylinders, but if it's such that when you follow the orbits of the endpoints of the non-full cylinders, that those orbits are all finite, life's not so bad, and you'll still be able to work with the notions of the Adler-Folklore theorem. So we want to relax that condition of finite orbits. I want it just to be such that the orbits stay out of some full cylinder. Okay, so this is the notion of the bounded non-full range. And this occurs, for example, for the exceptional set when we look at the Nakada alpha continued fractions. This also occurs in our situation. We have a similar exceptional set that for each one of our countable number of groups, when we go through and do an alpha deformation, that there are matching intervals, there are complements to them, and on those complements we have this notion of bounded non-full range. So I'd like to announce some sort of theorem. This is very recent work with Core. So, and your speaker had to try and put it onto some slides, so I appreciate your patience with me. So for example, here are the hypotheses. We've got the usual sort of map I want to think about. We have the calligraphic T is for the two-dimensional extension, and suppose we just check that we have a reasonable two-dimensional system, and so that is, first of all, that the vertical fibers are all bounded and they have true positive Lebesgue measure. In particular, in the alpha, in the Nakada alpha continued fractions, we know that every fiber contains some subinterval, contains an interval, and there's certainly a bounded length as well. And that's true also for our families. Where am I? I also want to avoid this zero in a denominator. And then I want to have at least one full cylinder that gets pushed so that I'm ready again. In all of these natural extensions that Core has been showing me for 25 years or something, there are plenty of full cylinders which come in and simply give you some bounded fraction of the fibers that it meets. So we'll want to have that, and then this bounded non-full range. And so some of those things were simply to have our region to be a finite measure, non-zero. We'll be able to prove that T is eventually expanding. I'm happy about that, of course, because there are plenty of non-expansive maps that we have. We get the ergodicity, and we also actually check that this planar extension is really a natural extension. Sorry about that. No more natural extensions you can say, but we want them. Okay, so maybe I shouldn't just tell silly jokes. Okay, so I repeat, we want to take and relax some of the standard conditions for Adler's folklore theorem, but we replace it with conditions on this planar extension. So let me sketch some proof of this. We go to the Lebesgue situation, so the very peaky look. And now the condition on fibers gives a similar condition on fibers. So I have that all of the vertical fibers are bounded. Maybe I should read what I wrote. And furthermore, of course, this is the cx plus d to the minus 2 versus cx plus d squared. That the nice thing about the Lebesgue coordinates for this sort of argument is that the vertical fiber over a single x gets hit with something whose derivative is constant. So that's very helpful for this argument. Number 3 is what I did say was number 2. Sorry. And now we have some full cylinder whose image is just coming across and giving us a bounded percentage of each of the fibers. And now, so what happens for the complement of the full cylinder? Well, the full cylinder is giving us some percentage. Every other complement has to be of bounded percentage because I only get 100% of the fiber. So let me say it differently by showing you a picture. Well, I see why all these other people had problems. Okay, so here's what I mean. So we take, say, cylinder -2 here. Cylinder -2 comes in, and for every vertical fiber, it gives us some portion of the fiber. Then I look at with Lebesgue eyes, and that's certainly still true. So I have some amount between rho and 1 minus rho was the number. Well, how about any other cylinder's image? If I take, let's go for a fiber here. Okay? Every other cylinder's image is certainly of bounded percentage in there, because I already got some piece of it. It's clear. So let me say this correctly. If I would speak slowly and clearly, you would nod your heads and say, my God, that's really silly. Right? So what it is that we hit every fiber with a bounded, clear percentage, and everything else that comes in is bounded away from giving us the full measure of the fiber. Oh, now I have to fast forward again? Well, that was too far, of course. I'm curious what comes up. Okay, so I repeat. So we have one full cylinder that we easily checked as the right thing, and it blocks everything else from doing anything too silly. Let me try that one more time. Okay. And then we have that the derivative when each fiber is constant. So if my cylinder is giving me 25%, its image gives me 25% of the image cylinder. And so what this means is that when I go 2 steps, so F each, maybe come Mr. Schmidt. So F is for fiber. F sub x is the fiber at x. And now I take the map and I simply find that the percentage that comes from the image of a fiber inside the image fiber is preserved under applying this 2-dimensional map. I'm saying? Okay, and then we have some telescoping trivial algebra to show that. What that implies is that when we start out with a fiber and go 2 steps, then we have that it has to be contracted by this rho squared. And of course, the 2 there was just so that I didn't get too confused. This is true for any n, because again, the percentage is preserved because the fiber derivative is constant on the whole fiber. Derivative is constant on the whole fiber. And so what we find then from that is that when you go the right number of steps, that we have a bound on the size of the image of the initial fiber. There is an upper bound on fiber lengths. We've chosen things so that our image is less than a factor times our lower bound. And the conclusion is that there's some little r, so that this is the eventual. There's some little r, so that when we take r steps with the algorithm, that in fact we have contracted the fiber. We've contracted the fiber. So we go r steps, and the vertical fibers get contracted. But Lebesgue here is invariant. So if the vertical fiber is contracted, that means that at x, we're expansive. Okay, so the 2-dimensional situation really gives an easy way to show that this map has to be expansive, as opposed to wasting many hours watching little orbits of points and getting them to eventually do the right thing. Do not do that, believe me. Right? This is the way to go. So expansive comes again from using the Lebesgue coordinates and the fact that the derivative is constant on fibers. And thereafter, the very reasonable conditions. I'm a slow person. Okay, and now I want to prove ergodicity. I know about you, but I'd like to see what I have in hand first. So let's go back and see. Here are the hypotheses. And I want to prove that these hypotheses imply ergodicity. So we have the Adler, Fulcor theorem. So the problem is that I don't start out with full cylinders. I have to address that. The second differentiability is no problem in this situation. And so I want to, in particular, worry about getting full cylinders. So here we go. Yes, sir? I'll come to you. I'll repeat the question.
Have you used condition B? And can you explain me what it means?
Yeah.
I'm not sure I understand it.
Okay. The question was, yes. The question was, have I used condition B and what does it mean? And condition B, watch me go back. I'm starting to get the hang of this. Oh my God, I'm not. You told me not to do that. She said it beforehand. Don't hit this button. Okay. Condition B, though, I can tell you, this is simply the initial measure is dx dy over 1 plus xy. So this is simply so that we have finite measure. It's just a finite measure. Where are we? Thank you. Okay, so indeed, we use that for the finite measure. We had boundedness of the fiber, finite measure, and then some full cylinder that does the usual thing. That third condition really is what we always see. And now the bounded non-full range. This is, again, we have a priori some non-full cylinders. We look at the orbits of their endpoints, and they avoid at least one full cylinder. Okay, and that's definitely a hypothesis. It's not always the case. Oh, come on. Okay, so what do? We've avoided one full cylinder. Let's take that full cylinder. If you prefer, take the largest interval that contains full cylinders which aren't entered by the endpoints of non-full cylinders, and we're simply going to induce. We take the first return map from this full cylinder situation to itself, and our condition is such that this interval map has full cylinders. Okay, so it's a silly, the condition is almost artificial. The condition is simply so that our induced map has full cylinders. And now we had our planar extension in hand. How is it created? It's created by bringing pieces back into place. And so when we induce past the bad stuff, the non-full cylinder stuff, all we have to do is look up and we have the same piece, we have the corresponding piece of the extension we had over our full cylinder portion. So it's already been computed for us, and therefore it satisfies the conditions that we already had. So we know we're eventually expansive on this with this induced map, and so all we have to do is get the bounded distortion. So really, it's all set up to concentrate on what is the hard part. Okay, so let's see. You'll recall now, I can even recall now, that y goes to cx plus d quantity squared times y minus cx plus d with a c factor. And parts of that is there. Okay, so I need to, here we go. I take a first derivative, and that's cx plus d to the minus 2. I take the second derivative, and now I put the second derivative over the first derivative squared, and I'm to bound that. So you'll do the little calculation and check that I didn't make any silly errors. I have to bound this. I have to bound c times cx plus d. Right? That's just plugging in there. Please don't make me do that now. Okay, and this is bounded over all the possible cylinders. So that's what we're about to do. Questions? Okay. Of course, we're going to use Lubeck situation. And now what do we know? We know that our vertical fibers are bounded. So the y's take values in those bounded sets. The y values are bounded. The image is in those bounded sets. The images are bounded. So we have the terms are bounded that I've written. On the other hand, we have our derivative is such that we bound it because surely the shortest fiber can never be expanded to be greater in length than the longest fiber. So this derivative is bounded, but this derivative is the cx plus d quantity squared. Okay, so simply our fiber length bounds give us this second bound in number 9 in the slide. Oh, I'm done.
Are you doing it for the induced transformation or for the
Say it
Are
again.
you working on the induced?
I'm on the induced. That's right. Okay, so what happens? Thank you. So the question was, where am I at this point? I'm on the induced system, which has the full cylinders. The end of the proof here now is that's ergodic, but when the induced system is ergodic, so is the original one. So that's the line that should have been there. Thank you, karma. Yes. Okay, so once again, natural extensions, these extensions are worth using. Quilting. I'll say just a couple words, if I may, about quilting. Here's a picture from not the most cited Dutch mathematician, but I think the most famous Dutch person who has a PhD in mathematics, Jonica Smeets, one of our co-authors. So Jonica made this nice little picture. So here's the idea of quilting. You start out and you've put in all this work and you have some planar extension for a given alpha value. You'd like to get the planar extension for its next door neighbor, for a nearby value alpha star. And so what do? You say these systems are so close, I'm simply going to say that the two intervals have a big overlap, and then there's a little bit on the right end, say. I'm going to have alpha is given to us, alpha star is less. I'm going to start with the alpha system and build the alpha star system. So the first thing to do is you say, okay, this little black strip, whoops, I'm not going to say that. Excuse me, forward. This little black strip, that's what I get for trying to rush. I'm ready again. Okay, this little strip is not in this new system to the left, and therefore its orbit under my old system is also not. So D0 here goes to D1, goes to D2, goes to D3, and it would keep going, and I'd have to cut all this out. This isn't in the new system. On the other hand, what is in the new system is, well, I take and find what did go there. The points that went to this black D0, in the new system, they should simply go to the left end instead of the right end. Okay, so the old system's pre-image of this D0, this heads out to this A for addition. So D was for delete, A is for addition, and then we take the new system's orbit of that A. And we just put that in, and the silly thing would be to rip out the black forever and then put in the white stuff forever. But synchronization or matching is all about the idea that in good situations, you go finite amount in the forward orbit of these, and the next step, they actually completely agree. Okay, so that's synchronization, which is well studied at this point in time in the situation of the Nakada alpha continued fractions, and this happens in various of these deformation families. So let me repeat. I'm going to use betas for the partition on an I sub beta f, or t's here. T of x is equal to m dot beta, is ax plus b over cx plus d, for m beta is equal to a, b, c, d, the matrix. And now what happens is I'm imagining I and I star are my two intervals. They have some overlap. And I simply look for the easy situations where they agree completely, the two maps. The complement of that is some where digits have been changed. And then there's a two-dimensional region that fibers above this. And so what happens is that the D0 I was indicating a second ago, this is the image of the fibers above the changed digits. So C here, script C, is pushed by the old system to our strip that we have to cut out. Some notation, the endpoint orbits we have to follow, L's are for left and R's are for right, and stars are for the new system. Yes, a little vocabulary. So synchronization or matching is this, that after a certain number of steps, the right and left endpoints, the orbits agree, they match. Okay, and this is part of what's needed for this gluing together. Quilting, as much as certain co-authors of mine and of Wolfgang's really like this notion of quilting, it's only something that locally succeeds in general. We need extra conditions. So let me say it differently. Even on a synchronization interval, a matching interval, it's not true that you can actually quilt. What happens is that digits can start changing on you. So to tightly match or tightly synchronize is that the two systems assign the same digits to the orbits of the endpoints. Okay? And so that means I'm going to apply the same matrix each time to the fibers above them. So that's a very local kind of situation. When you have it, though, then what this says is that quilting is successful in that situation. That if after a finite number of steps, the two orbits coincide, then you can actually do this wonderful notion of just cutting out part of the old system. You cut it out until you wait for the new system to agree, to match and synchronize. So that lemma, I repeat, is that quilting is successful to pass from an old to a new system in the situation of tight synchronization. I'll have to stop at some point, right?
Yeah, 7 minutes.
Oh, I'll take a deep breath. I'll take some water. This is great. Oh, I took it wrong. Wow. Strong stuff, it turns out. What did you do to me? I'm ready again, excuse me. Okay, so in the situation that we have these, this will go away, I hope. In the situation that we have this successful quilting, in particular, various properties will be shared with these neighboring systems. So I want to sketch, if I can, before I absolutely lose my voice, that ergodicity is shared. And you know, I never really saw the ergodic theorem as a student, so I really love whenever I actually prove something's ergodic. I apologize for that, but that's really what these next couple of minutes are. It's like, wow, it's so fun. Okay, so I want to show that under the assumption that the old system is ergodic, so is the new, and it's another application of these extensions. Okay, so I'm going to use this quilting business. So I start out, number one must be that I have my putative invariant E on the set, which is invariant under the new system. What I know is that these two systems are so close that they agree on some piece. Okay? Well, of course, the old system is ergodic, so E cannot be contained on just that agreement. Of course, right? So, all right. So it's on something else. So it's on something else. Well, the something else is about the region fibered over where the digits change. C is for change again, yeah? So this E must live somewhere in the new system's orbit of the changed digit fibers. Okay, it's somewhere, but part of what I skipped while I was choking on water is that the orbit, one can really show in this tightly synchronized situation, the orbits of these pieces are disjoint. E is an invariant set, so it must be following the orbit of these new added pieces, which in particular means because of the quilting succeeding, that there's synchronization, and it has to actually come into the old system. It must be somewhere on here. All right, that's right in there. We've come in and agreed with the old system. This is our ergodic system. So on the other hand, we're in the old system. We know that E has to be meeting the new system, so it must get there from passing through the region fibered over the changed digits. So what we should do is create some invariant set for the old system that's related. I mean, once I started the game, that's what I had to do. Of course, in the right system is simply we've got the invariant set for the new system E, and then we know that it meets the changed digit fibers. We push this along in the old system, and after one more step, it comes back and agrees with the new system. But what a weak here, because of course we have that is an old system invariant set. The old system was given to us to be ergodic, and so this has a zero measure under how I surely set it up, and therefore so does E itself. So I tell you, it's like a great little exercise for students. And since I didn't do them as students, I thank you very much for indulging me. So there are going to be other deeper, more interesting properties that naturally come with you when you have this tight synchronization. And here's just the fun one for me. Thank you very much. It's not true, I repeat, that we have this bounded non-full range for all points. So what we fortunately have is I'm in the Nakada alpha continued fraction situation. We have that the exceptional values of alpha do have this property, and this is because you get to them by, you start on a synchronization interval, and there's a folding process where the digits of, say, the left endpoint get repeated, and you get longer and longer strings of these digits, but there are only finitely many of the digits in the alphabet that you're using at that point. So the exceptional points are such that the orbits of the two endpoints only use finitely many digits, but there are lots of full cylinders around. So there's certainly full cylinders that these non-full cylinders never enter. This is also true that endpoints of synchronization intervals have periodic endpoint orbits, again, finitely many digits, so we have the boundedness. And then, and then we can use the quilting. It's a local process. We've got lots of situations where we have the bounded non-full range, and it's simply when the orbits of the endpoints go to zero and get stuck there. Well, that's true in this situation for all rational alpha, and so you give me something which is doesn't satisfy the non-full range. I can come arbitrarily close and catch it with the tight synchronization. So this spreads the ergodicity everywhere, and so it gives, if you will, the two-dimensional method for showing the ergodicity of all of the Nakada alpha continued fraction maps. The same thing happens for R's, and thank you.
Are there any questions? Henk?
Just some short questions that I to confirm that I understand the picture.
Sure.
So this map on the natural extension, this was a T hat, I believe.
Yes.
So that is eventually expanding in all directions.
Yes.
It is not Markov.
A priori not.
But it has this synchronization, except for the exceptional set.
Okay, I was trying to click back to see things. So, let's see.
Yeah, that one.
That one? Okay.
For
Something
example,
like
there
this.
was
For
another
example.
one earlier on. Yeah.
Yes, we can go back if you wish.
Okay, so
Okay, could you repeat your question? I apologize.
so this map T hat is eventually expanding.
Yes.
Usually doesn't have a Markov potential, but
Correct.
for most parameters has this synchronization.
Yes.
And another question is when you look at the invariant density of your original continued fraction map, is that piecewise Möbius, the density?
The density.
When you project down.
Yes. Understood. I just thought I'd buy time by looking at a picture. Which are right in here.
these cases,
Yes.
but you have disconnected things.
Yeah, thank you. Exactly, thank you very much. So here I've put us in a situation where the family of these generalized alpha continued fractions are actually quite simple, because the maps here that I'm using all have determinant 1. So they're orientation preserving, etc. But thank you, sir. In the traditional Nakada alpha continued fraction, in fact, the determinant can be -1. And in that case, you'll see fibers which are not simply intervals. And so this will cause great difficulties in achieving exactly what you said.
Okay.
So it would be sum of Möbius contribution. I mean, when you have a rectangle in this picture, you integrate over the measure 1 plus 1 over 1 plus xy squared, and so you get.
Yes. So the comments are about the invariant measure on the interval map is given by taking the marginal measure here.
You know what it is.
So if I have some set downstairs, I assign to it the measure of the fibers above it. Yeah.
Yeah.
Did you answer your question, or you want?
I have a question. So this theorem that you said, so in principle should also work for other triangle groups, right?
Absolutely, yes. That was the hope, was that this would be a handy tool to have, right? That under these somewhat reasonable conditions, we get, in particular, the ergodicity. Yes. Yeah.
Okay. But you haven't checked yet, but it should work. More questions?
Oh, okay. You want to? Yeah, so this is a sort of, I'm ready to answer your question. No, we haven't checked for all groups. What happens in particular is we really can get nice models for all of the triangle groups. So we'll want, of course, a triangle group that has a translation in it. So now I have to look for all mn infinity groups. What happens is, so if we have, wrong way, of course. There it was. Thank God. So here's the sort of phenomenon that gets really complicated in general signature, is we're going to have many pieces like this. Right? And so you're going to have multiple non-full cylinders, and you really have to follow this around. The two-dimensional things are looking rather complicated. And also what happens, I know I have to stop very soon. What happens, and that's really quite interesting in these alpha families, is when there's matching, when the synchronization, there's some relation that occurs. And the question is, which relation happens, and how does the group / continued fraction algorithm choose that one? And in this case, the relation that drives the matching in this situation is not that seen in the classical alpha continued fractions, and also, in fact, there are two different relations, one in the previous slide situation and one in this two-piece needing to apply this element C twice. I presume that as the n parameter goes to infinity, that you see lots of different relations. I'm quite curious as to what drives that.
Any more questions or comments? Otherwise, let's thank Tom again. Cool.
Thanks.
We'll resume at 11:15.
The title of the talk will only cover part of the talk. I didn't want to talk 45 minutes on this, but it's good as a title. And it's models coming from applications, but don't ask me about the applications. So what you should think about is that you have a population with different, say, genetic types, M genetic types, and what you have is a distribution of the different types, the occurrence of the different types in your population, and a map from this distribution to the distribution at the next generation. That's the map, where is it, V. So it's distribution, so the state space is the simplex. Non-negative numbers adding up to 1. And there's a certain map from one population to the next. This could be all types of maps. This is a simple type of map called the Volterra operator. Here the principle would be that if you have genetic types, for the next generation to find the type K, you need parents, one of the parents needs to have type K also. And if you then look for quadratic operators, you would find formulas just like this. The one you can read as the sum of xi, so it's a quadratic operator called Volterra operator. And this is like an analog of Lotka-Volterra differential equations, but then discrete time dynamical system. Here is one particular simple kind of Volterra operator that will appear in the next slide. In the result I will quote extreme Volterra operator, where these guys are
It has to go to delta n, and some conditions have to be set.
Oh, yeah, I mean, it's conditions so that this is a map from the simplex to the simplex. I didn't want to write down what precise conditions. It has to make sense as a map from the simplex to itself. That's all I wanted to say here. Yeah. Yeah. Yes. Yeah, so the extreme operator is just this one, the cave operator. That means that if you start with only a distribution with only type K, you will of course stay type K, and otherwise you will converge to the opposite side, opposite simplex, very fast. Yeah. Then here's the result. I quote the first result. I'm not going to study dynamics of a single Volterra operator. I will take random Volterra operator. So an iterated function system where, so from in time I will have slightly different Volterra operators. So an iterated function system of Volterra operators. And the question is, what dynamics will these iterated function systems of Volterra operators have? And here's one result. So iterated function system, or not necessarily finitely many maps, but there's a probability distribution on the space of these Volterra operators with a condition that these extreme Volterra operators are picked with positive probability. And you pick them IID from this distribution, and then it turns out that almost surely orbits will converge to vertices of the simplex. So dynamics is very simple. This is for these quadratic Volterra operators, random iterated function systems. And I will discuss a bit, say the next possible class of systems you could study, cubic operators. So you take cubic operators from the simplex to itself and consider iterated function systems of those. There are lots of possible cubic operators thinkable. We got this system from actually, so the author is, the type of system was studied by Yamilov. He handed us these population dynamics, genetic dynamics type systems. And he also handed these particular systems, not all cubic systems, but a particular one parameter family of them with some symmetry involved, cubic operators depending on a parameter theta. I'm restricting now to the two-dimensional simplex triangle. One can also do this on higher dimensional simplices. The formulas get nastier. And in fact, we didn't want to study the dynamics anymore. We didn't think it was worthwhile. But it's probably along the same lines as what I will tell about this one. So the setup is the same. There's a probability distribution now on these maps, so on the parameter theta, and you pick them IID, and you iterate the operators. And the question is, what happens? What these single maps do is fairly simple. They are maps from the two-dimensional simplex to itself. There was this parameter theta from 0 to 1. If theta is 2/3, you can check that the map is just an identity map. And if theta is larger than 2/3, the dynamics is like this. So you have 7, I think, fixed points, the vertices of the simplex. The center point is a fixed point, and the 3 midpoints are also fixed points for the map. The vertices are stable, the center is unstable, and these midpoints are saddle points. And the similar for theta smaller than 2/3, but the stability is reversed. So the center is stable, and these guys are unstable, and the midpoints are still settled, but stable and unstable is reversed. And the question is, what happens if you pick these maps at random from an iterated function system?
Is there a correspondence? For instance, can you say that for some theta, 2/3 of the dynamics
It's like the inverse of the...
with time reversed?
I didn't try to check, so I'm not sure. It may be, I don't know. I mean, the result is basically the same, that almost surely orbits converge to fixed points. But I'll instead of stating that shortly, I'll put some terminology around it.
Certainly not if you mix the inverse and the forward.
You need to, the theorem will, I'm not quite sure what the question is, but the theorem will come.
One of them is the inverse of the other.
I didn't say that, but
No, but are you fixing the parameter? Or?
no, the parameter will be taken random, IID. Yeah. From some distribution, and what you get, of course, depends on the distribution. If you have a simple case, where is it? A simple case, if the distribution is supported on, say, theta bigger than 2/3, you would only iterate maps of this type, which is not very exciting. So the more interesting thing is if you have probability of thetas, to pick thetas both bigger and smaller than 2/3. So here's the more general notion. The statement will be something like orbits converge almost surely to fixed points. So you don't really need this, but the general notion would be that of a random attractor. There are lots of notions of random attractor possible. Pull back, forward, set attractors, point attractors. This is the notion of forward point attractor. What you do is, so here the notation, you have a sequence of thetas picked at random, so that's denoted by omega, is fairly traditionally. For omegas, you would have a set in the simplex, which is invariant, and you would converge to it iterating forward in time. Points would converge to it iterated forward in time. That is a canonical thing to think of for a forward point attractor. Point is just meaning that you start iterating with a point. In random dynamics, people also start iterating complete sets and see where they go. With this definition, the entire simplex would probably also be a forward point attractor. You want a minimal one to which points really converge. And then in this case, you have a result similar to the previous one, that if you have a probability distribution from which you pick the parameters, not the point to vert itself, then you would only be iterating the identity map. Then the minimal point attractor consists of the set of fixed points. So that just means that almost surely iterates of a point converges to one of the 7 fixed points in the simplex. One can also ask if you take a point, to which of the fixed points will it then converge? So to talk about that, this is again the picture of the simplex. There was this symmetry, as you may have noted from the picture. These lines are all invariant. So there are in fact 6 invariant triangles in the simplex. And we only need to study the dynamics on one of these triangles. So this is the symmetry, the rest is all the same. So G1 is one of the little triangles in the simplex, and orbits would then converge to to the center, to the saddle, say, the random saddle, or to the vertex E1. And so this is trying to answer the question to which of the fixed points orbits converge. So for a point x, one of these fixed points, A of x is the domain of attraction. If you start in A of x, then with positive probability you will converge, to x. Yeah, so x will be one of the fixed points, and A of x is the domain of attraction. If you start from there, you have positive probability of actually converging to that fixed point. Then the dynamics is mostly determined by the Lyapunov exponents. What you see here, this expectation of the log, these numbers are just the derivatives of the linearization at the fixed points. So for instance, at the vertex, go back to the picture, here the derivative is a multiple of the identity. So you have a double eigenvalue, so you also have double Lyapunov exponents. The same is true for the center, double Lyapunov exponents, and at the saddle you have 2 Lyapunov exponents. And if say this one is negative, the Lyapunov exponent at E1, then the basin of attraction, say, from anywhere in the triangle, you can actually converge to E1 with positive probability. The same is true for the center. If the Lyapunov exponent is negative, from anywhere in the triangle, you can converge to the center. And for the saddle, it's also kind of the same. There are 2 different Lyapunov exponents, but they could both be negative. Even though for single maps, this is a saddle with positive and negative eigenvalue, but randomly, the Lyapunov exponents, the expectation in both could be negative, so it becomes an attractor. The random saddle becomes an attractor. And in fact, from anywhere in the triangle G1, you can converge to this attracting random saddle. Yeah, these Lyapunov exponents being negative, that just tells you that if you start close to a fixed point with positive, there's a stable sets. There are stable sets. So if you start close to the fixed point, you will actually converge to the fixed point with positive probability. This statement says that you can actually start anywhere in the triangle G1 and still converge with positive probability to a fixed point with negative Lyapunov exponents. But this is really due to the specific formula of the map. This is not a general statement. This only holds for this specific cubic operator. The interesting thing is, I think, or one of the fun things here, is that all these, depending on the distribution, all these numbers could be negative. So you can find the distribution mu from which you pick your parameters at random. then all these Lyapunov exponents become negative. I think this is, for instance, the case if you start with an interval symmetric around 2/3, 2/3 minus something to 2/3 plus something, and take the uniform distribution from there, then all these Lyapunov exponents will be negative, and from anywhere in the triangle you have positive probability to converge to any of the three fixed points, In a dynamic language, I see this as intermingled Bayesians. If you would write the system as a skew product system, as a dynamicist would do, then it's over sequences of the random parameters times the simplex. Then you have attractors, which are the products of the base space, the sequences of the random parameters times the fixed point. So that type of attractors. These attractors have their Bayesians of attraction, and the Bayesians of attraction all lie dense in the state space. So 3 Bayesians of attraction, and the closure of all of them is the entire state space. But this is in the probabilistic way to formulate that.
But the probability of, say, landing in E1 depends on X, right?
Yes. Yeah, if you start absolutely. If you start close one of them.
Which depends on
yes.
Because the conditions
Yes.
on the right hand side only depend on theta, which is
Yes. Yeah.
kind of
Yeah.
nice.
Yeah. Note also that so these fixed points can be attractors if the Lyapunov exponents are negative. It is somewhat clear that if the Lyapunov exponents are positive, they will not be attractors. You move away from them. It is a priori not entirely clear what happens if the Lyapunov exponent is 0. But the theorem tells you that if the Lyapunov exponent is 0, then such a fixed point will not be an attractor. So 0 Lyapunov exponents, you also move away. I have a couple of more slides on different systems, so I move away from these quadratic operators, but on different systems which have 0 Lyapunov exponents, so to try to give an idea of what happens when you have 0 Lyapunov exponents. It's not particularly interesting in this system. If you have somewhere 0 Lyapunov exponents, there will always be one of the fixed points will always have negative Lyapunov exponents. You will always converge to some of the fixed points. So there's always something with negative Lyapunov exponents, and if another fixed point has 0 Lyapunov exponents, you still converge to the one with negative Lyapunov exponents. So these 0 Lyapunov exponents don't do a whole lot. You just converge to something else. But in other systems, you get more interesting phenomena, intermittency, if you have 0 Lyapunov exponents. So I wanted to discuss that in the next couple of slides, which is no longer covered by the title of the talk, but add something, I hope. So this is just the comment written down that I just said. I want to tell something about 0 Lyapunov exponents. And I'll start with a basic example, random walks. But then non-homogeneous random walks. So what I wrote down here is again an iterated function system. Now particularly simple, just 2 maps where you pick both with certain positive probabilities. It's on the interval 0, 1. The blue map moves down to 0, the red map moves up to 1, and you compose them at random IID. What happens for the dynamics depends again on the Lyapunov exponents at the fixed points, whether you have a drift towards or not away from the fixed points. So these are the Lyapunov exponents. The average of the log of the derivative at say 0 is L0, and at the other fixed point 1 is L1, the Lyapunov exponent at 1. And the interesting case is where a 0 Lyapunov exponent occurs. In the previous system, this was on a simplex, so it's a higher dimensional version of this. This is now on the interval. But in the previous case, if you had at one fixed point 0 Lyapunov exponents, then you would have negative Lyapunov exponents at least one of the two other fixed points. Here I'm taking, so that would be L0 is 0 and L1 would say still be negative, so that you would converge to 1 with with full probability. That's not so interesting. The interesting case is where the other fixed point is repelling on average, has positive Lyapunov exponent, but 0 Lyapunov exponent at 0. In that case, the dynamics is what physicists shows on-off intermittency, shows an intermittent effect. I'll go back to what's written here, but I think I have a picture here that might make clear what happens. This is a time series in a case where there's a 0 Lyapunov exponent here and a positive one here. And time series, you see that iterates can stay close to 0 for many points can stay close to 0 for many iterates, but then they will burst away from it and come back and stay again close to 0 for many iterates. That is called an intermittent effect, where in fact almost surely if you calculate, so if you take if you take a small neighborhood of 0, a small interval 0 to epsilon, say, and you calculate the proportion of points in an orbit that are in this interval, then this has full density. So you're almost always near 0, but you don't stay there. There are also infinitely many bursts away, so there are infinitely many iterates outside of this small neighborhood. So with full density in a small neighborhood of 0, but infinitely many bursts away, and then you come back. Yeah, this type of thing is many of you will have seen this in several other contexts, like Pommeau-Manville, and in this case it has been called by physicists on-off intermittency. It's basically because in the skew product system you have an invariant manifold. The base system times 0 is an invariant manifold, and you stay close to the invariant manifold often and go away every now and then.
Can you estimate the excursions? How long it would take?
I think there are, I'm not quite sure if we could do that, but in physicists certainly have estimates on that, yeah. Yeah, this is really not that fancy. The iterated function system was on the interval with fixed endpoints, so you can simply map the interval 0, 1 to the real line. 0 becomes minus infinity, 1 becomes plus infinity. And then you have walks on the line, but the walks are non-homogeneous. Where you go depends on where you are. It's not a group action, but you have a standard random walk plus some perturbation. But in this situation where you, and that's perhaps an advantage from not starting on the line, but starting with smooth maps on the interval. If you then go from the interval to the real line, you will get non-homogeneous random walks, but they are exponentially close at minus infinity to a homogeneous random walk. So very close to minus infinity, it looks like a standard random walk, but there is a small perturbation away from it. Yeah, but this exponential closeness makes the analysis of the random walks a lot easier. Being very close to standard random walks makes it fairly easy to bound all kinds of stopping times for excursions. People in random walks have also studied such non-homogeneous random walks with larger perturbations. There's Lamperti in the 1960s already did that and figured out exactly transitions from this intermittency to more complicated, to other things, how big the RI should be. Zwaar. then there's a next step would be to generalize, to go away from iterated function systems. This type of phenomenon might occur in general. The picture I have in mind is that in some dynamical system you have an invariant manifold. Maybe I should make a... so this is the blackboard is the state space. There's an invariant manifold in the state space. There's some invariant measure on the manifold, but in the transverse directions you would have 0 Lyapunov exponent. You could have. So the manifold is not normally hyperbolic, but it could be invariant for some reason. And in transverse directions, it's on average neither attracting nor repelling. One might expect, or at least that would be my feeling, that typical dynamics, if there's a possibility, if you go away, that you come back, typical dynamics would spend lots of time near the invariant manifold, but have excursions away and then go back. This type of intermittency phenomenon, which I don't know how to handle in this generality. But here is an attempt to understand it in a simpler case, where the invariant manifold is a circle. And this is so first by picture. The system here is in the base. It's no longer a shift on symbols that you would have for iterated function system. It's a expanding circle map or interval map here by a factor 3. I would like the doubling map, but in a computer doubling maps don't work very well. So multiply by 3. And something in the fiber. This term here actually corresponds to if you would, so the fiber is 0, 1. If you would map the fiber to the line, this would be a random walk with steps -1 plus 2y. So depending on where you are in the base coordinate is y, you would make a step -1 plus 2y, which on average is 0. So this part would be a random walk. But I'm adding a perturbation. I'm not in the co-cycle context. I'm adding perturbations. I'm in skew product context. So that I do not change, because of this x squared term, the Lyapunov exponent at 0, but I make the Lyapunov exponent at 1 positive. So 1 is repelling, 0 has 0 Lyapunov exponent, and the picture should convince you that you have an intermittent dynamics situation here. Orbits spend most time near 0, but have bursts away from it. So this is the context one would like to study is expanding maps on the interval or circle in the base. You would look at perturbations from random walk. So there's a random walk where you have a step psi, depending on y, depending on the base point. The average step you take is 0. So no drifts at plus and minus infinity, but you add perturbations to make so plus infinity to make 1 repelling, or plus infinity to create a drift away from it. So the Lyapunov exponent at 0 is just 0, and the Lyapunov exponent at 1, I want to make that positive by this perturbation. Oh, yeah. If you want, you can try to pronounce it. So this is a PhD student, Rabodunandria Nandraina. I had to practice quite a bit, but there's music in it, right? So And the result is that indeed there is an intermittency phenomenon, just like in the random walk context earlier. So if you take, for some mysterious reason, I've now chosen an interval epsilon 1, so a complement of a small interval near 0. Take a point in 0, 1. For the proofs somewhere, the M, so the expanding map in the base, has to be sufficiently expanding. So M as 2 will not always do, at least there are some technical difficulties for us. But then for almost all Y, you will find that the average the density of points in U is 0. So the density in a small neighborhood of 0 is 1. And also that you are infinitely many iterates not close to 0. So it's the intermittency phenomenon. The full density are close to 0, but you don't converge to 0. You don't stay in the small neighborhood infinitely often. You are away. To get at this result, so this is not random walks. It's not iterated function system, but we will approximate it by something similar. So first, it's as in the previous case, it's useful to look at fibers that are real lines. So I just map the interval 0, 1 to the real line. And then the system is a perturbation from a random walk with steps xi plus the perturbation. But coming from this context, starting with a smooth system, means that the perturbation is again exponentially small when you're near minus infinity. So it looks like the standard random walk, or I don't know, I shouldn't call this random walk perhaps, but this one, it looks like a co-cycle close to minus infinity. Yeah, then our strategy was to approximate by Markov random walk. So you take Markov partitions on the circle. You take Markov partitions by small intervals, so fine Markov partitions by 2 to the n little intervals. That would give a subshift. So the expanding circle map would give the subshift on the Markov partition. And you would use that to rewrite and then approximate the system. So what we start with is what physicists have been calling a chaotic walk. So you have this walk with steps depending on the y-coordinate, and the y-coordinate is governed by a chaotic dynamics, by the expanding circle map. So this is a chaotic walk, and it's not co-cycle, it's not a group extension. I'm adding perturbations to it, like so. You write that as a instead of the expanding circle map as in the base system, it's measurably isomorphism, a subshift of finite type using this fine Markov partition. And then you can approximate replacing this by a single step on this little interval where you are in your fine Markov partition. Yeah, this is this I think I said before. Yeah, so then the real step and the step that replaces it are very close, comparable to the size of the interval of the Markov partition. The perturbation is still exponentially small near minus infinity, so that's the context. And that means that, so what happened is the chaotic walk, a walk driven by an expanding circle map, is now approximated by a Markov random walk, a walk driven by a subshift of finite type. And if you use finer Markov partitions, you get better approximations. And at least for these Markov random walks, there are standard ways to calculate stopping times for excursions, say back to or away from a neighborhood of minus infinity. The trick there is to formulate and solve a Poisson equation. I'm just writing down something, just stating that it is possible for a Markov random walk to, by Poisson equation, go to this walk and then calculate, that's a martingale, and then calculate stopping times. But that means that you need to understand somewhat the solution of the Poisson equation. And we do this for sufficiently good approximations, sufficiently fine Markov partitions. So everything depends on the fineness of the Markov partition. The n, if you have 2 to the n little intervals on the circle. And I'll end with some pictures of what this solution to the Poisson equation looks like that shows up in the altered random walk. And here this is for the standard random walk. So if you take just steps, say +1 and -1, if you are in the so the base is the interval 0, 1. If you are in 0 or half, you would take step +1. If you are in half 1, you would take step -1. That's the standard random walk with just 2 possible steps. You could write that as instead as driven by a Markov partition with more symbols, fine Markov partition, and then you get a Poisson equation which looks like, the solution looks like this, which is essentially something like the difference of, so these are, say the different cylinders, the different symbols that you find in 10 subsequent symbols. And this is something like the difference of the number 0 and the number 1 in these first 10 digits of symbol sequences. That is something that appears, but you show that you see that the solution of the Poisson equation is unbounded in capital N. So that is something we have to worry about in taking n high. That's one thing I wanted to mention, and the other thing was just I wanted to show this pretty picture, as well as one more picture for different xi's. So if you start with different steps, you get different solutions to Poisson equations. So this is another graph of a solution for if the step is something like a cosine, then the Poisson equation looks like this. And it's actually because of having to deal with this solution and our inability to do that properly, that we need little m to be high enough, that we need a sufficiently expanding map in the base that gives us more information of what the solution to the Poisson equation looks like, so that we can take limits of capital N go to infinity in the analysis. This is not very helpful, but just telling that it's something we have to worry about. This was basically what I wanted to tell. So I'll put down again this picture of the typical time series for on-off intermittency. Thank you.
Questions?
It's a very simple question. You started with the Voltaire, I think, and then you moved to this. So what's the connection that you get attracted to a fixed point in a sense, or you stay in a neighborhood?
Yeah, so I wanted to, so the Volterra things, you could have, one thing I wanted to make clear is that zero-Lyapunov exponents is an issue you have to worry about. I didn't want to spend more time on zero-Lyapunov exponents here, But you have the dynamics is similar. If you have a zero Lyapunov exponent, typically you will spend long times near the fixed point, but then there is a burst moving away. But because there is another attractor, you will then at some point move to the other attractor. So you don't see the consequence of zero Lyapunov exponents. You don't really see in this system. But I wanted to make it clear with other systems where you would see the consequence of zero Lyapunov exponents, the intermittency.
Okay.
It's just I apologize that it's not in this system.
Okay.
Henk.
Since you were showing those time series on a few pictures further, can you actually reconstruct the dynamics from the time series using some Taken's reconstruction theorem or so?
I don't know, but there's I don't know, but there's certainly the time series here look like there are frequent bursts away from zero, but that is just because I put it in my simple little laptop. Mm-hmm. In reality, these bursts are very infrequent. So there are plenty numerical issues. If you do good numerics, there are lots of numerical issues, which would also make reconstruction very difficult in practice.
Yeah, so going back to what Karma asked at the beginning, so do you expect to have, for instance, if you fix the neighborhood of the fixed point, can you say that the number of times you're out of the neighborhood is logarithmic in n or something like this? Is that what you would expect? Because you get full density of staying inside, right? So my guess would be that the excursion is logarithmic in time.
I can't give you the formulas, but there's certainly in the physics literature there are formulas for the expected for distribution of, say, the laminar phases. So that the times that you're close to zero. I don't remember, so I can't tell you what it looks like. I'm not sure if we can prove anything in our systems.
Mm-hmm.
But in model systems there are formulas, so there's something that can be done. Yeah.
But and also the solution to this Poisson equation is it continuous or not?
But here it's no, the solution depends on where is it?
So the first one really doesn't look continuous. But the second
no, it's
one,
not. Nothing is no, it's not continuous. Certainly not. I mean, it's a discrete function anyway, because in the base you have the cylinders, so the symbols of the Markov chain. So there's 1024 symbols.
Yeah, but in the limit.
But in the limit, so in the limit this looks like some fractal thing. Yeah. But also in many cases in the limit it will be some fractal thing. It's not continuous. I take that back. I don't know.
But maybe it's Helder continuous for some cases or something. Yeah, it could be, but I don't know. Yeah.
Yeah, I don't know. I can't speculate. It's very interesting.
Yeah, maybe adding the perturbation helps, in fact, to make this more regular. I don't know. Some speculation. That's it.
The question occurred to me also, but I don't know. Yeah.
More questions? Well, let's thank Ali again. The last talk is
With Dalia Tehesiu and Mike Todd, and but first I want to, at a certain point I need to explain to you what this Fibonacci map is. But first of all, let me do an example to motivate a bit. So this is going to be the Pomo-Manful map, and the graph is like this, and here's the second branch, and this has this neutral fixed point over here. Pomo-Manville. And I know that P is after the M, but this is really how they do that in the paper. Okay, so f of x is either x times 1 plus 2x to the power alpha, or it's 2x minus 1, and this is when x is less than a half, and this is when x is more than a half. And it's known that these maps always have an invariant measure which is absolutely continuous. That's mu. But this is finite only if alpha is less than 1. Otherwise, it's an infinite measure. So if we want to study all kind of properties about these things, the way to do is to induce to the domain of the second branch. So let's do a nice color. Red. So you're going to look at the first return map to that. So I just iterate until I get into that box, and to be far away from this neutral fixed point which is creating the problems. And then you get something like this. And you get infinitely many branches. And this one, so this is the induced map. So let's call that F bar. So bar will in this talk always mean inducing. So this is F to the tau, where tau is the first return map. And this one preserves a nice finite absolutely continuous measure. Let's call that mu bar. And to derive all kind of properties that you would want to know, it's important to estimate the tails, and that is these types of quantities. And for that, it was already mentioned in Dalia's talk yesterday. We're going to look at pre-images of, say, a half. Let's say we call that x1, is in this case a half, and we take pre-images of it. So you walk this staircase down to the left, and you say xn is that, and you want to know how large xn is. Now there are very specific or very detailed estimates, so I'll just copy one, and this is the most detailed that I could find, and it's actually from a paper of Dalia, Hitoshi. So xn is what, a half beta to the n to the power beta. Oh, by the way, beta will be 1 over alpha, in case you wonder. Plus beta plus 1 over 4, 1 plus beta log n over n to the 1 plus beta minus some constant beta to the squared over 2 1 n 1 plus beta plus big O of log n over n 2 beta, and here we have a square. And I only write this down to illustrate how difficult it is to get these things. I mean, it's a lot of work to get to a formula like that, but on the other side, you sometimes need that. You sometimes need indeed this type of precision, and therefore there is some cheat avant la lettre, and that's the second map. So, oops. If you don't want to go into that problem or that trouble, you could just say...
Hey, I'm sorry, could you remind us exactly what xn is?
Oh, okay. So I take x1 is a half, and then x2 is the left preimage of it, and x3 is the left preimage of that.
And why you change alpha to beta 1 over alpha?
Is there some significance in this?
Well, there is no deep significance, except that the formulas will be slightly easier if you write beta instead of 1 over alpha constantly. So it's just notation. Statics, if you like. All right. So I'm going to do another map, which still has this right branch, it's the same. And then I'm going to do a cheat. I don't want to compute these things, I will just choose them. So I just choose a sequence of points converging down to 0. And then I'm just going to make a map that has precisely the property that x2 is the preimage of x1, x3 is the preimage of, and that thing is called the Gaspar-Wang map. And so it's going to, and again you can induce that. So you can again induce, and the map will look like something like that. We'll have all those linear pieces. And then if you induce, this will have linear pieces as well. So that makes your life quite a bit easier, because then the induced measure is simply Lebesgue. Okay. Okay, so this is in fact a countably piecewise linear version of the first one. So can you remember this acronym? Because otherwise I will write it down for you. Okay, countably piecewise. Picky. Okay. Okay, so now with these kind of ideas in mind, I want to describe what is the Fibonacci map. Okay. So I start with a unimodal map, and I want to do it like this. F goes from, in this case, -1 to 1, and has the formula where the exponent L is some, need not be an integer, some real number bigger than 1. And that thing looks like this. So 0, which is the critical point and hence C, goes to 1, and then it kind of looks like this. And here is C again. Oh, I see. Thank you. So 0 goes to 1, 1 goes to 1 minus A, and okay, then you have a unimodal map. And you can see two, let's call them Z0 minus and Z0 plus. Those are the 2 points that map to the critical point.
But maybe there is no A.
Maybe there is. Some parameter.
But wait a minute. If x is 1, then you go to 1 minus a. Are these not going down to? They're not starting from 0, right? Or so these are not.
And this here is 1 minus a, and if a is less than 2, this is slightly bigger than minus 1. Yeah, I could be 2. Then, but we'll find out what a is. Okay, so you have those 2 pre-critical points. Well, then on this interval, there is a first iterate and a point that also maps to C. And that I want to call Z1 minus. So that says, okay, after, all right, so we have ZK. Well, you can do this again and again. Okay, you get the picture. So this point, after some number of iterates, maps to C. And you do this inductively. If you do this inductively, so Z0 would map after one step to C. Z1 would map after probably 2 steps, and so on. So what I'm doing here is inductively defining both a point Zk, which was minus, and actually the same is true on the other side. So there's Z0, Z1, plus, and so on. And I'm defining iterates, namely precisely that lowest iterate for which this happens. Okay, and these SKs are called cutting times. Now, in the case that in that case, when these cutting times are exactly the Fibonacci numbers, then I want to call this the Fibonacci unimodal modal map.
And that depends on your special choice of A.
And that depends on the special choice of A. It's not a golden mean.
If you pick A equal to 2, you get SK equal to K, isn't it?
Yes, you do.
Okay.
Or K minus 1 actually, but or plus 1, whatever. Good. Okay, the next thing that we did was induce. So we don't like that critical point because there's not expanding. So maybe we can induce to get away from it. And the way to do that, or a way to do that, is, okay, here I have Z0 minus again, Z minus, Z0 plus. And I'm going to say my induced map, this here, when I restrict to this interval, I think I want, doesn't really matter, K minus the K plus 1 minus union K plus minus plus K plus. If I restrict to that interval, I want to use exactly this iterate. And if you do that, then you get something that looks like this. Alright, here's sea level again. And then it turns out that you get 2 branches downwards, and then another 2 branches downwards, and then 2 branches upwards, 2 more upwards, 2 downwards, and these branches are getting smaller and smaller and smaller. It's just what happens. And but it starts to be expanding, and that's good. And actually, it does have an infinite Markov partition, because these points zk minus and zk plus, they define a Markov partition. So that's good. What's not good is that these branches are not linear, and there's not always too much control of the distortion. And the other thing that I don't know is how, or not, maybe not precisely enough, is how fast these points zk plus or minus decrease to 0. Okay, then I'd use the same cheat as with the Caspar-Wang map. I'm just going to force it that way. So I'm going to take some points, and I'm just going to say this here, plus or minus is lambda to the plus or minus lambda to the k, where I just choose some lambda between 0 and 1. And I'm going to write down these points. So this is 0 plus, 0 minus, and now these points go down to 0 in the middle, exponentially fast. And I'm just going to copy this picture, but now with linear branches. So it looks like this. Sea level. And it turns out that you can cook up a countably piecewise linear unimodal map such that you induce it, you get exactly this thing. And that looks like that. And that's the one that I can handle. Well, you see maybe that this is some a bit superfluous, right? I mean, there's some symmetry here. Left and right are the same. So there is actually a 2-to-1 cover where we factor out this symmetry, and then we get a map on where you can scale it to 0, 1 again. That looks like this. Oops. Now the trick is to do the segment line here and then do branches like this. And these points are lambda to the k.
So you're actually something like
I fold it over.
folding it
Yeah. Yeah.
in both directions.
Okay, so this is sometimes called the Stratmann because they were the first to actually look at this map in detail. But the ergodic properties of this one is the same as the ergodic properties of this one.
So the endpoints are always on the line, and what is the slope of the line?
The slope of the line is 1 over lambda.
No, the slope of the invisible one.
I don't know, the slope of the invisible one is invisible.
No, you know, because to draw that picture, you draw a line.
Okay. Okay, this was lambda. And now I just do a straight line from here to the corner. So let's do the corner a bit better. And take that one out. So, is that better?
Yeah,
I think he wants to, if you draw a line joining the endpoints of these lines, you get a line? Like
Yes, I get a line. All these endpoints lie on the same line, which is drawn here invisibly.
okay, and where does it end? What slope?
At the corner here. This is 0.
And other does it, the slope of the invisible line plays up roles depend on...
They just helped me to draw this picture in a decent way, but apparently not with much success.
Okay, and the slopes are the same?
The slopes are the same, except I think this slope is a bit different, but all those other slopes are the same. Okay, right. So why are people interested in Fibonacci maps?
Started with that map.
Okay. So why are people interested in Fibonacci maps? So properties of Fibonacci maps. Well, you could look at the omega limit set of the critical point, which is actually the same as the, in this case, the closure of its forward orbit. This is a minimal Cantor set. And if you look at the restriction of your unimodal map to this set, this factors out to well, a circle rotation. And now I can finally please core, because what is gamma? Is the golden mean. All right. Some more properties. And that's why I brought in this L. Depending on what L is, the ergodic properties of this map are entirely different. So, now let's see where I am. F has a finite invariant measure if L is less than 2 and a bit. It has an infinite invariant measure if L is larger. So there are some constants, I don't quite know what they are, L1 and L2. If then L is between those values, then this mu is infinite and conservative. And if L is really large, then this system is no longer Lebesgue conservative, and what happens is that this Cantor set becomes an attractor. That is to say, for Lebesgue, almost every starting point, if you start to iterate, it converges to this Cantor set. And now, as I said, I don't quite know what these numbers are. I think L3 is 8 is good enough. But here's one thing that is nice about this one.
L1 is greater than 2 plus epsilon.
Probably, yeah. But it's nice about this family that in this case I can exactly tell you where that happens. So this is when I can exactly tell you if I look at my notes. Yeah. This is when lambda is small. This is when lambda is intermediate. And this is when lambda is big. All right. Now, one more result that I mention here, just because I can mention my co-author, which is Jane. Well, on the attractor itself, suppose we're in this case, this is a Cantor set that factors out to golden mean rotation. But what happens to all the points in the basin that are convergence to this omega limit set? Okay, so then we have something. So if omega c is the attractor, then the maximal automorphic factor of indeed the entire interval with this map is the same circle rotation. Okay. Oh, maximal automorphic factor is, well, a factor is just a factor. Automorphic means you can invert it. So it's the largest factor map on which the dynamics is invertible.
Ah, okay.
Okay. Okay, so but now let's go to the topic of the talk, the thermodynamic properties. So for that we need some potentials. So let's say phi, and I want to take the log of the derivative. That is the geometric potential. Psi is some other potential. And then the pressure, thermodynamic pressure, can be defined as the supremum over all invariant measures of the entropy of the measure plus the integral of phi plus s psi in u. So that is something that people in thermodynamics are very much interested in, what that thing looks like. So let's try to draw a sketch, and this is the sketch that you would get. Oh, one more thing. It's okay if I take this one. This is an okay example, and this is what I'm going to sketch now. So here we have the parameter s, and this is p of s, and it looks like this. Now here I have scaled in such a way that if I plug in s is 0, this is 0, which you can always achieve by saying instead of phi, I just subtract something. Okay? Well, where u is the pressure of 0, because this is linear or additive. And then we are very much interested in the shape of this pressure function near here. Now, why are we interested in that? Well, for one reason, knowing about the shape of this pressure function gives you information about limit laws of ergodic average of psi. And another thing is that if you take the Legendre transform of this pressure function, it gives you information about multifractal properties of the system. Okay, so what is that? So how would you get to that? Well, you can indeed use inducing again. And so let's do some notation for inducing. So we had the induced map, and we're going to take induced potentials. So this is going to be J is 0 tau minus 1. Induced potential is just the ergodic sum. And since I took the geometric potential here, minus log of the derivative, this just ends up in being minus log of the derivative of the induced map. Okay? Well, at some point I was subtracting u, so then I would get this here, and in that case you just have to subtract u times tau. It's just the same thing. Okay? And now then Abrama's formula helps you in relating the shape of the pressure of the original system to the shape of the pressure of the induced system. So it's basically telling you that this here is this here for the induced thing with some scaling factor, and I'm doing this a bit sloppy, but what you have to do is to integrate your induced time with respect to the measure. Well, here I'm a bit sloppy because exactly which measure do you use? Well, you use an equilibrium state for the induced system, but you integrate the induced time, and these are how they're related. But this gives a problem well, I erased it, but it gives a problem, for example, for the Pomo-Manville map, if alpha is bigger than 1. Because then this thing, so this is problem if this denominator is infinite. So that's more or less where our theorem is giving the solution. So how do you do this? Relate the pressure of the original system to the pressure of the induced system when you're looking at an infinite measure, when this integral of tau is infinite. Okay. So if I'm lucky, I can state the theorem before the end of the talk. Theorem. So let's assume that the induced map has good properties. That is to say, it's a Markov map with full branches. Of a reasonably good shape. And then we have two parts. If I'm really lucky, I will get to the, I get to state my hypothesis before the end of the talk. But this is something about the tails, and this is something about psi. So if I have those two conditions, then there exists an explicit C star, which is a constant, and an explicit function that goes to 0, such that P of this thing, that is the shape of the original pressure, is C star shape of the induced pressure to the power 1 over beta. Well, maybe I should call this alpha just to please Mike. And then I have an error term that is this form. And B, if H1b and H2, then there exists explicit C1 and C2 and Q of S also going to 0, such that the thing that I want to estimate is between bounds. And then you ask, why do I do an error term when it's just less than a constant anyway? But that's in the explicit. I know exactly what constant it is. And then error terms make sense. And it's less than 2. Well, 1 plus Q. Okay?
Does this QS go to 0 fast enough, or the speed plays a role? It doesn't matter.
I don't think that the speed plays a particular role in this result, maybe in speed of convergence of this, but I'm not quite sure. We can discuss later. I mean, is whether the speed of how fast this goes to 0 has any, but this Q of S is given by the system. So once you put up the conditions, the Q is given, so you don't have much choice, I think. All right. It depends on the tails, yeah. So, conditions. So 1 over beta. Thank you. Okay. This is a horrible picture. Okay, so what are these conditions? Well, tail conditions. Okay, so here we have the beta again. This is the main term, and this thing is order n to the minus 2 beta, and n times bn should be regularly varying, and this thing is order n to the minus psi, where psi is bigger than 2. Okay, now let's state H1b. Well, in this case, you have these tails between two constants of this order. So that's to say, this here is less than C1, n to the minus beta, and more than C2, n to the minus beta. And now those constants in the theorem relate directly to that beta and to the constants over here. And the C stars and so on depend explicitly on those constants and the form of Q also. Okay. Now this theorem, I mean the A version, let's say H2, this is something about psi. That is to say, how tame it has to be. Well, it's actually not worse than your induced time. It shouldn't go to infinity or so, faster than your induced time. And then based on these conditions, you can, well, based on these conditions and the fact that your induced map has full branches, you can derive particular properties, spectral properties, of a twisted transfer operator. So if R is your usual transfer operator for the induced system, then I'm going to twist it with two parameters. The S is the same as that S, and the other is the potential shift, so to say. This here is the normal transfer operator e to the minus u tau e to the s psi v. And well, if you know what the transfer operator is, good for you. If you don't, I don't think this 5 minutes will enlighten you too much. But I mean, it's at the heart of proving a thing like that, that you have really good control of that twisted transfer operator. Okay, so I hope we kind of understand now the content of the theorem. And if you look at part A, well, that applies directly to something like this, to the Pomo-Mantel map. And in the infinite measure case, and actually that's what I drew here. So what I can say is that theorem part A, what we got there, improves on a result of Lopez from 1993, where you had some estimates of this shape. What we get is better. And then the B part, Well, hopefully that has to do something with the Fibonacci map. And yes, it does, but I hope you see the problem. It's in the first line of the theorem. No full branches. So what do we do about that? Okay. That means we have to reinduce. And yeah, I wish I had drawn this picture better, but let's look at this set and we call it V0. And I want to look at the first term map to V0. So I had already one bar, and now the next bar is for the reinducing. So this is going to be the minimum n bigger than one, such that if I iterate the first induced map n times at the point x, I enter the set, and the double bar, so the reinduced map, is this, the first induced map to this one, but that was f to the tau. That. All right.
It's not equivalent to inducing on V0 from the beginning?
Let me finish my, then maybe you get it. So I have this here, and now I'm using that block. This should be a nice square, okay? Ah, I see. I need to go to the diagonal. Okay. Anyway, let's take a different color. And all these branches are linear, but they have more than one accumulation point. It's not like the Pomo-Manville map. So what do we know about it? Yeah, well, the reinduced measure in this case is just Lebesgue, right? So that's nice. What is also nice is that right. What is also nice? Oh yeah, the number of branches that here is 1 over n plus 1, 2n over n, and maybe you recognize this. This is the nth Catalan number. All right. What is also nice is that the tail of mu bar tau bigger than n, that lies between C2n minus beta, C1, oh, I used that order, right? N to the minus beta, with beta is log 1 minus lambda over lambda divided log gamma. And if you remember, if Corey remembers what gamma was, that was the golden mean. Well, this is very nice. Point is that it is useless. Okay, I'm going over time, but okay, I can raise this. Because this is the tail for the wrong measure. So let's call this f of the actual thing that we have is some new induced time. Let's call it rho. So rho is some kind of product of these ones. And if you want to compute it exactly, is the blue okay? Okay, hard to read. Okay, go back to white. Rho is tau star is the sum, j is 0 tau bar minus 1 of, well, ergodic sum of this one. So T composed with F bar J, and if you write it in a different way, and now the composition is in the index. So basically what I'm doing is an ergodic sum of Fibonacci numbers. And now there's the real crux. How on earth could you compute this ergodic sum of Fibonacci numbers? Well, the proposition is that if I look at the tail of this one, the thing that I really need is that yes, this is indeed between two constants, and if you do that, the beta does not change. The constant changes, of course, but this doesn't change. And to do, well, this is simple. If you look at the previous papers, well, one of these previous papers is something by Mike Todd and myself, where we have a first estimate of the pressure function of this creature. Now this theorem that we have improves on it, but from that older paper we get things like this, but the hard thing is doing this, and that's indeed 4.5 pages hard computations. And with this I would like to stop.
Questions or comments? No?
So in your theorem that you just rubbed off, you said part B there was you had explicit C1 star and C2 star that were giving you upper and lower bounds.
Mm-hmm.
If you drop the explicit, do you know there is some constant which you're equal to this constant times all your stuff?
I mean, are you asking if you're not trying to get the explicit constant?
That's right.
Does your life become easier?
Yes.
I think hardly. Yeah. I mean, yeah. The technical behind. Okay, you just don't have to write down precisely what does this constant mean, but to get to a constant is just basically as hard as to get to an explicit constant.
Okay.
I mean, what you're getting is for the linear system, right? But
Yeah.
you cannot, and this was like an approximation of the original ones. Can you get information from the linear to the original thing?
We live in hope.
Okay, let's end this with the hopeful note. Anybody else?
Well, I mean, it's a bit better, I think. Well, we still live in hope, but one thing by using this reinducing is that whereas this one, the distortion properties are really bad, especially when L is big.
Yeah.
And we don't really know how big it needs to be because we don't know what the L1 and the L2 was in my story. But the distortion properties if you get here, those are good. So, at least some hope.
Okay, so I think that's it for this wonderful conference. Let's thank Henk.
Well, before I switch off the microphone, let me extend, I guess on behalf of all the participants, our thanks to the organizers, still standing, yeah, there are two of them, for a wonderful conference. And, well, let's have lunch.